February 8, 1942. Jakarta Airfield, Java. The Boeing B-17E Flying Fortress, serial number 41 to 2471, lay abandoned on the rain-softened tarmac, its fuselage streaked with mud from a crash landing, its American star still faintly visible beneath a hastily painted Hinomaru. The crew of the 7th Bomb Group had fled just hours earlier, ahead of advancing Imperial Japanese infantry sweeping through the Dutch East Indies. Though damaged, its nose section torn away, engines missing, the airframe remained largely intact. To the soldiers who discovered it, this was a trophy of conquest, proof that Western air power had faltered before Japan's lightning advance. But to the engineers who would soon study it with scientific rigor, this bomber would become something far more consequential, a mirror reflecting not American vulnerability, but Japan's own industrial limitations. Over the next 3 years, as specialists from the Koku Jujutsu Kenkyujo, the Air Technical Research Institute at Tachikawa, dissected this aircraft and others like it, they would confront a truth so unsettling it could scarcely be spoken aloud in official reports. The United States had achieved a level of manufacturing automation, standardization, and systemic reliability that Japan's artisanal production model could never replicate. The B-17 was not superior because of its aerodynamics or firepower. It was superior because it was built by a civilization that had mastered the art of producing complex machines not as individual masterworks, but as interchangeable units of industrial output, rapidly, consistently, and at scale. The discovery began in earnest in March 1942, as Japanese forces completed their swift subjugation of the Dutch East Indies. At Madiouin Field in Java, engineers found B-17E 41 to 2471 in remarkably sound condition despite its missing components. At nearby airfields, Malang, Cheribon, Bandung, 3 more flying fortresses awaited in varying states of disrepair. Tereo Saito, an aviation editor for the Asahi Shimbun, toured these captured bases immediately after the occupation and documented the scene with journalistic precision. He counted 4 B-17Es being prepared for technical evaluation, noting that Bandung Field appeared to be the main maintenance base for the Americans, and that it was here that technicians from the Gaiken, the colloquial name for the Air Technical Research Institute, conducted their initial assessment. The Gaiken, headquartered at Tachikawa Airfield near Tokyo, represented the apex of Japanese aeronautical engineering. When word reached the capital that intact B-17s had been captured, the institute dispatched technical teams without hesitation. Their mission was not merely to reverse engineer an enemy weapon, but to understand the industrial ecosystem that had produced it, a task that would prove far more humbling than any tactical analysis. Restoring the bombers to airworthy condition was a monumental undertaking. The B-17E was the most advanced variant of the Flying Fortress deployed to the Pacific at that stage of the war. Its electrical architecture, hydraulic actuators, and engine installations were vastly more complex than anything in the Japanese inventory. Using parts salvaged from multiple wrecks, and aided by captured Allied mechanics pressed into service, Japanese engineers spent months painstakingly reassembling 2 B-17Es. They pored over U.S. maintenance manuals, translating technical jargon and deciphering American engineering logic. By late 1942, they had succeeded. 2 B-17Es were flight-ready. A third, a B-17D captured earlier at Clark Field in the Philippines, had already been flown to Japan. The decision was made to transport the Java bombers to Tachikawa for comprehensive evaluation. The journey, spanning thousands of miles through newly conquered territories, required meticulous coordination, fighter escorts, a Nakajima L-2D mothership, a licensed copy of the Douglas DC-3, and advance notifications to every anti-aircraft unit along the route to prevent catastrophic friendly fire. In May or June 1943, the 2 B-17Es landed safely at Tachikawa. Japan now possessed 3 operational examples of America's primary heavy bomber, not as relics, but as subjects for forensic industrial analysis. Major Kazuyuki Saito of the Imperial Japanese Army Air Force led the evaluation team. An aeronautical engineer with deep experience in aircraft design and testing, he assembled a multidisciplinary cadre, Lieutenant Shiyama and Lieutenant J.G. Kurusu handled structural analysis. Army Assistant Engineers Shimamura focused on airframe integrity. Major Uno and Captain Yagi served as test pilots, and Army Engineer Kaneo led the propulsion team. Their mandate was absolute: document every aspect of the B-17's design, construction, operation. Crucially, the Japanese had recovered complete U.S. technical manuals, meaning no system would escape scrutiny. The examination began with the airframe. Engineers measured rivet spacing, panel thickness, and spar dimensions across all three aircraft. What they found defied the foundations of Japanese manufacturing philosophy. Rivet holes aligned with near-perfect consistency between different bombers. Wing ribs from one aircraft fit seamlessly into another. Control surfaces, ailerons, elevators, rudders, showed identical forming characteristics. This was not the work of master craftsmen adapting parts to individual airframes, as was standard practice in Japan. This was systematic mass production using standardized components manufactured to precise, repeatable tolerances. In Japanese factories, no two aircraft were truly identical. Parts required hand-fitting. Repairs demanded artisans who could modify replacements to match the specific machine. The B-17 suggested a different reality. Any component built to specification would fit any aircraft of the same model, without adjustment, without calibration, without delay. Nowhere was this more evident than in the engines. The Wright R-1820 Cyclone radial engines powering the B-17 consisted of hundreds of precisely machined parts. Japanese engineers disassembled multiple examples, measuring clearances down to thousandths of an inch. Crankshafts, connecting rods, cylinder barrels, pistons, all exhibited near-identical dimensions across different engines. The U.S. manuals confirmed the implication. American mechanics in the field were expected to replace major engine components without fitting or fine-tuning. A cylinder from one engine would install directly into another. A crankshaft was interchangeable with any other of the same model. This stood in stark contrast to Japanese practice. Japanese aircraft engines were assembled by master technicians who hand-fitted components to achieve proper clearances. Field maintenance required highly trained specialists who understood how to adjust tolerances on the spot. The American system eliminated that need by embedding precision into the manufacturing process itself. Quality was not the product of individual skill. It was engineered into the tooling, the dies, the automated lathes. The same principle extended to every subsystem. The hydraulic system used standardized threads and identical couplings throughout. Any actuator could be removed and replaced without modification. The electrical system employed machine crimp terminals instead of hand-soldered joints, enabling rapid replacement of entire wiring harnesses by mechanics with basic training. Even the oxygen regulators for the crew bore manufacturer stamps from automobile parts suppliers, firms like Bendix and Stuart Warner, companies with no prior aviation experience. This revelation was profound. American industry was so deep, so mature, that firms producing carburetors or brake lines for Ford and Chevrolet could seamlessly shift to making precision aircraft components. The bomb shackles were self-adjusting mechanical devices requiring no calibration, unlike Japanese racks, which demanded careful tuning by armament specialists. And the defensive armament, 13.50 caliber Browning M2 machine guns, though crudely finished by Japanese standards, functioned with robust reliability. Their loose tolerances, considered unacceptable in Japan's precision-crafted weapons, proved advantageous in combat. They resisted jamming from dirt, cold, and vibration. Any armorer could maintain them with simple tools. Japanese aircraft guns, by contrast, were delicate instruments requiring expert care. By autumn 1943, all three B-17s were flying regularly from Fusa Airfield near Tachikawa. Japanese pilots gained first-hand experience operating the heavy bombers, documenting performance, handling, and operational procedures. The aircraft appeared in military training films, repainted with U.S. insignia and sometimes escorted by a captured P-40, to simulate realistic intercept scenarios for Ki-43 and Ki-44 fighter pilots. These films were shown in public theaters as propaganda, depicting Japanese fighters triumphing over American bombers. But the pilots knew the truth. Even in simulated attacks, the B-17's overlapping fields of fire, structural resilience, and ability to absorb damage made it a formidable opponent. More troubling was the strategic implication. For every B-17 shot down, American factories would produce replacements faster than Japan could replace its own lost fighters. In February 1943, the Asahi Shimbun published Anatomy of the Enemy's Aircraft, a comprehensive technical analysis featuring extensive B-17 diagrams and photographs. Mitsubishi engineer Hisanojo Ozawa, designer of the Ki-21 and Ki-67 bombers, contributed an article acknowledging that while the B-17E was based on a 1935 design, improvements had made it a first-line combat aircraft, and that the original design had been extremely good. Kawanishi Shirzwa Kikuhara, designer of the H-8K flying boat, noted the bomber's sophisticated systems integration and simplicity of cockpit arrangement considering the plane's size. What these analyses carefully avoided stating outright was the most disturbing conclusion: the B-17's superiority lay not in its design, but in the industrial system that produced it. Destructive testing in early 1944 confirmed this. When one B-17E was destroyed in a ground collision at Fusa, engineers seized the opportunity to cut into the wing structure. They measured hundreds of rivets. Diameter variation was less than 0.0002 inches. Installation depth varied by less than 0.0001 inches. Such consistency was impossible with hand riveting. The aircraft had clearly been assembled using automated or semi-automated equipment. The implications were strategic. If American factories could produce B-17s with this level of precision, they could produce them rapidly. If parts were truly interchangeable, field maintenance became dramatically simpler. If workers needed less skill because precision was built into the tooling, production could scale quickly by training new laborers. Japan faced the opposite reality. Skilled craftsmen were in short supply. Training a new aircraft mechanic took years. Increasing output meant finding more masters, not adding more assembly lines. By 1944, the evidence was overwhelming. American aircraft production reached 96,000 units that year. Japan produced 28,000, but the gap in combat effectiveness was even wider. American aircraft, built with interchangeable parts, could be repaired in hours and returned to service. Japanese planes, hand-built and non-standardized, required days of skilled labor for even minor fixes. Boeing's Plant 2 in Seattle alone produced 6,981 B-17s. Douglas and Vega added another 5,750. Total production, 12,731 Flying Fortresses. Japanese engineers, studying serial numbers and manufacturing dates on captured bombers, could extrapolate approximate production rates. The mathematics were devastating. If America could build heavy bombers this quickly, its fighter output must be staggering. Japan had entered a war of industrial attrition against an opponent with 10 to 20 times its manufacturing capacity. The strategic bombing campaign that intensified in 1944 sealed Japan's fate. B-29 Superfortresses, larger, more advanced successors to the B-17, appeared over the home islands in unstoppable formations. Precision raids destroyed the Nakajima plant at Musashino, Mitsubishi's facilities at Nagoya, and Kawasaki's factories. An earthquake in January 1945 further crippled Mitsubishi's supplier network. Japanese aircraft production collapsed, from 2,500 airframes monthly in May 1944 to barely 1,500 by early 1945. After the surrender, the U.S. Strategic Bombing Survey toured Japanese factories and confirmed what perceptive engineers had already deduced. Japanese production relied on skilled manual labor, limited standardization, and inconsistent subcontracting. At Mitsubishi's Nagoya plant, American inspectors saw craftsmen hand-forming aluminum panels that would have been die-stamped in Seattle. Manual riveting predominated where American factories used automated systems. The survey concluded, Japanese aircraft factories had been organized appropriately for producing hundreds of aircraft. American factories had been organized for producing hundreds of thousands. Yet the story did not end in defeat. The engineers who studied the B-17 at Tachikawa carried its lessons into the post-war era. They understood that matching American industrial power required not copying products, but adopting production systems. Over the next 2 decades, Japan transformed its manufacturing base. Craftsmen shifted from building individual items to designing precision tooling and automated processes. Companies like Toyota, Sony, and Honda embraced systematic efficiency, developing innovations like just-in-time manufacturing that refined, then surpassed, American mass production. By the 1970s, Japanese factories were producing automobiles and electronics with quality and efficiency that stunned the world. The irony was profound. In the 1980s, American engineers toured Japanese plants to learn the very methods their own wartime industry had inspired. The captured B-17s examined at Tachikawa were destroyed in the war's final months, by bombing or deliberate demolition. But their legacy endured. They taught Japanese engineers that modern industrial warfare is won not by superior craftsmanship, but by superior systems, not by building better individual machines, but by building adequate machines in overwhelming numbers, not by relying on master artisans, but by designing processes that enable ordinary workers to produce precision goods at scale. The B-17 dropped 640,000 tons of bombs in World War II, but its most decisive contribution may have been the silent lesson it delivered on a Java airfield in 1942, that industrial organization, not battlefield valor, decides the fate of nations. In manufacturing classrooms today, the story of those captured bombers remains a case study in how examining an opponent's product reveals the invisible architecture of their power. The engineers who measured rivets and documented tolerances in 1943 became the architects of Japan's industrial rebirth. They had learned from aluminum and machinery that modern industry belongs not to those with the most skilled hands, but to those with the most effective systems. And in understanding why they lost, they discovered how to win the peace.